Merci beaucoup. Thank you very much to the organizers and to ESUS for this lovely conference and the invitation. So I'm going to talk, what?
For the weather too.
And the weather. It's going to improve. Exactly.
But you know, we don't need to be out. So
Exactly.
Right, there's a motivation to come inside. So I'm going to talk about Einstein equations. I'm going to introduce some geometry into our PDEs. And of course, we all heard about the detection of gravitational waves. So it was confirmed in February this year that it was detected last year in September. And I'd like to make a connection to, let's say, geometric analysis and what we know from the PD point of view, analyzing the Einstein equations. What can we say about gravitational radiation from the mathematical point of view? So basically, I'm going to introduce first, well, what do we mean by space-time? What are the Einstein equations? And so again, this will be a point of view of PD of this hyperbolic set of PDEs from a geometric viewpoint. I'm going to make a connection with, so what do we mean by energy in GR, general relativity? So this maybe not a straightforward notion to think of from the beginning, so we have to think about it a little bit. I will talk about what I will call null infinity. So let me just very heuristically motivate this for the moment. So if we think of gravitational radiation, so they are produced during the merger of compact binaries like black holes, for instance. So there's something happening here. We have two bodies, black holes, spiraling in. They lose energy into the gravitational field, so they radiate waves. And these waves will travel at the speed of light along so-called null hypersurfaces. So you can think of this as a generalization of a light cone, basically. So this will go along null hypersurfaces. Let's say when we are far away, when t goes to infinity, so we can think of where we are sitting in an experiment. So this is null infinity. So we will look at null infinity. That's where we are sitting when we're doing experiments, and we are looking backwards in time along these null hypersurfaces. So we would like to understand from a point of view of analysis and geometry, how does our space-time look like out here, and what kind of information can you gain from what's happening in the past here, for instance, in such a source. I will explain this a little bit more later. And well, of course, gravitational waves, I'll also address something called the memory effect. That's a permanent change of the space-time by the gravitational waves. And we also hope that this will be detected in the near future. And detection is one thing we hope, of course, for the future, that this will be a new tool to really learn about other parts of the universe where telescopes cannot see. Okay, I'll then address some results in the asymptotically flat case. So that's where we look at galaxies, for instance, or we think we are here, the galaxy creates curvature, but far away, the next galaxy is so far away, so we can assume the space-time is flat far away. Another setting is the cosmological setting. When we look at the whole space-time, the whole history of the universe, what can we say there? Well, first of all, what is a space-time? So we look at the Einstein equations. So on the left-hand side, and I'm going to talk about 4 dimensions, so 3 plus 1, 3 spatial, 1 time dimension. So we look on the left-hand side, so we have basically the geometric objects, if you like. So we have the Ricci curvature, the metric, we are solving for the metric, the scalar curvature, and we call this G mu nu on the left-hand side the Einstein tensor. And on the right-hand side, so we plug in the so-called energy momentum tensor. So whenever you have electric fields present or a fluid or anything else that is not given by gravity on the left-hand side, so you plug it into the energy momentum tensor, and you have also to supply the corresponding equations. So for instance, if you have electromagnetic fields, you couple your Einstein with the Maxwell equations and you get the coupled Einstein-Maxwell system. So we are solving the Einstein equations for the metric. We'd like to create the space-time, either locally or globally in time. And well, we'll see. So it's possible now to, if you have the Einstein equations, we usually write them as, well, if you look at it this way, it looks nice and compact, but we usually write them as a system of hyperbolic nonlinear PDE. And well, if you add the cosmological term, so how does cosmology come in? Well, Einstein in 1915 had written down his equation without this cosmological term, but then he wanted to study cosmology, and he was actually looking for a static universe at the time. He didn't believe in anything that's moving. The universe had to be static. And to counteract gravity, he then plugged in this lambda term, which is giving you an expansion, basically. So he got a static universe by doing that, but for all purposes now, so we think since the 1998 observations that our universe is actually expanding at the accelerated rate, and this is modeled then by this lambda term. Okay. And often I will just look at the Einstein vacuum equation. So if the right-hand side, your T mu nu is 0, the Einstein equation is reduced to the Ricci scalar of the full space-time being 0. And there's already a lot of interesting information or questions you can ask about just the Einstein vacuum equations themselves. Okay, well, first of all, in order to study anything that has to do with real physics, we would like to do a mathematically rigorous problem, of course. You have to study the Cauchy problem. So it all starts with the Cauchy problem for the Einstein equations. And as most of the audience is not working in GR, with some experts as an exception, so let me review a little bit what does it mean to set up the Cauchy problem for the Einstein equations. So it's a bit different in various ways. So an initial data set, what is that in GR? So we think first of all of a three-dimensional manifold. So you can think of T equals 0. You get a Riemannian complete manifold. If you look at asymptotically flat, for instance, that you're interested in. So you get a complete Riemannian metric, the induced metric on the initial hypersurface. And we specify a symmetric 2 tensor K. Maybe I'm going to write it down. And if you have anything on the right-hand side present, so other matter fields, you also specify, of course, these equations. Now, the Einstein equations couple into two sets of equations. One is the constrained equations, which the initial data has to satisfy. And the other set of equations are the evolution equations, the ones you then solve into the future. And so the constrained equations, you cannot just pick any initial data, but it has to fulfill these constraints, and only then you can think about doing an evolution problem. And then a Cauchy development of such data is given as a globally hyperbolic space-time of this sort, verifying the Einstein equations and the embedding given as these things. So maybe just to say at time equals 0, so we think of some space-like hypersurface H, 0 for instance, G bar and K. And this initial data has to satisfy the constraints. And so if I have a time vector field, I can introduce that. So this K is going to be the second fundamental form with respect to T then. Well, let me first talk about asymptotically flat systems, as I just motivated a few minutes ago. So if you look at what happens, for instance, within a galaxy or a cluster of galaxies, you think the next object is so far away, you think your space-time is going to be flat very far away. So what does that mean? So we think of asymptotically flat initial data in the sense that outside of a sufficiently large compact set, so H without K is diffeomorphic to the complement of a closed ball in R3. So and then the G bar, the metric G bar and K have to decay G bar to delta Ij and K to 0 fast enough. And of course, I will make this more precise. So what type of decay, what type of asymptotically flat data we are looking at. So let me first say that, well, if you look at the history of general relativity, and so the Einstein equations were put out there in 1915, and it took, well, there were many things happening in between in math and physics, but it took until the 1950s and 60s where Yvonne Jacques-Brouillard and Bob Garage actually really solved the well-posedness for the Einstein equations. If you look at, for instance, in 1919, we have Eddington's experiment confirming the bending of light, etc. You have on the physics side of GR many of these big things that happened, or the expansion of the universe found by Lemaitre in 1927. So all these things, you have many of these successes, and mathematically you could ask, well, what's been going on mathematically? There were many people actually working, like Luret, Schauder, many people looking at the initial value problem, but it's not that easy to figure out what should be exactly the right way to put up the initial value problem. So I'm skipping all this history, but it's actually interesting to read up on that. So there's many people who contributed in many ways. So basically in 1952, that's the first rigorous general mathematical theorem in terms of well-posedness. So Yvon-Jacques-Briand then showed that if you take Hg bar k as such an initial data set, which is, well, here this is formulated for the vacuum Einstein equations, but it's been generalized to hold for most other fields on the right-hand side. So then there exists a space-time satisfying the Einstein vacuum equations, with H into M being a space-like surface with induced metric G bar and second fundamental form K. And then the general form of what, so whenever you do solve the Einstein equations, so basically you go back to one form of these well-posedness results for these local results. So then the other formulation is given here. So Yvon-Jacques-Briand and Bob Gerache in 1969 then came up with this formulation of the well-posedness. Okay, so that's the first rigorous step in general, I would say. Well, let me say something about energy in GR. Well, most of us, well, when we think about PDEs, so often we need to find, of course, energies that have to be controlled to get control on the solutions of our equations, etc. So if you think of doing something like that in GR and you take the most naive approach, so things might fail. So what's the problem here? So one problem or interesting feature is that if I'm sitting at the point in GR, I can actually transform away the gravitational field. So by transformation, I can make it zero. So how would you define energy at the point if you can actually transform away the field there? Well, that's one problem. So you can think, well, maybe I don't look at the point, maybe I go a little bit further, maybe I integrate over a sphere, something quasi-local. Well, it turns out that's one thing we can do, but also for asymptotically flat systems, for instance, what's been understood quite well for a lot of interesting space-times is you can integrate, for instance, over a space-like slice, or you can also look at if you integrate locally over a sphere and you get some mass or energy, expression, and you can take the limit, like the Hawking mass, I'm going to write that down later, and you take the limit to null infinity, there's something else called the Bondi mass, for instance, that will show up later. So there are mass and energy definitions for certain, actually many interesting space-times that we understand. But let me give you maybe a little bit of an idea of the confusion at the beginning by citing Einstein and one of his colleagues. So Einstein formulated some sort of an energy momentum theorem very early actually for a closed universe. And so most of his colleagues at the time did not agree with it. And here is what he says. So here this is a citation. While the general relativity theory was approved by most theoretical physicists and mathematicians, almost all colleagues object to my formulation of the energy momentum theorem. I'm not going to go into details, but he wanted some kind of an energy momentum conservation for some closed universe. But turns out that's maybe not the right way to do it. And so this is Einstein with Georges Lemaitre. Maybe a side note, there's actually Georges Lemaitre, a Belgian mathematician and physicist who derived from the Einstein equations and Slipher's observations in 1927 that the universe is expanding. It was not Hubble. Hubble had a paper 2 years later and he never talked about an expanding universe. Okay. Let's still stay a little bit more with energy and conservation. So what do we know? So we can look at the Bianchi identity that we know from geometry and apply it here to the Riemannian curvature tensor. And well, we take, for instance, twice constructed Bianchi identity and get this equation on the left-hand side of the Einstein equations. And then, of course, this implies by the Einstein equations themselves an identity of this form. So people at the beginning also thought, well, is this energy conservation? Yes, no. Does it make sense? Well, it makes certainly sense of some sort, but to call this the energy and energy conservation is probably the wrong thing to do in GR. So maybe one more thing about that. So Noether's theorem, if you think of it a little bit more in a generalized way, well, what are we looking for? Within some setting of a Lagrangian theory, we always look for a continuous group of diffeomorph transformations which leave the Lagrangian invariant, right? So to such an object, we have then a quantity which is conserved. And in GR, the first problem, if you have a most general space-time, you don't have any symmetries. So what are you looking for if you don't have any symmetries at all? However, nature is usually better than just the most general case. For instance, if you look at an asymptotically flat space-time, your background Minkowski space has a lot of symmetries, and you can start looking at maybe certain isometries you can preserve basically in a way or another in the manifold or control. Well, here is maybe one more slide where Einstein, Hilbert, and Weil struggled over these energy components of the gravitational field. So they were thinking about this very hardly at the very beginning. And here's just one more quote by Hermann Weil. This is in his book Space, Time and Matter of 1921. And he looks at these components here. So he says, well, nevertheless, it seems to be physically meaningless to introduce this TIK, so that's the Einstein pseudotensor based on some specific Lagrangian he had there, as energy components of the gravitational field, for these quantities are neither a tensor nor are they symmetric. So in fact, by choosing an appropriate coordinate system, all these TIK can be made to vanish at any given point. Although the differential relations referring to the divergence of the Einstein pseudotensor being zero are without the physical meaning, nevertheless, by integrating them over an isolated system, one gets invariant conserved quantities. So you see there was a lot of thinking, reflection about what the right energy notion should be, and already one suggestion is, oh, well, maybe we should integrate something over an isolated system. So that was already a good idea then. Okay, but let's now jump to more modern days, well, modern 61. And so if we think of one type of notion of energy and momentum, so this is the ADM energy, linear and angular momentum that is was introduced in 1961 by Arnowitz, Dazer, and Misner. So basically, this is the definition, but the way you think of this, you integrate these geometric objects basically at the sphere, over sphere at infinity. So you let R go to infinity. So you're in one space-like slice, and you integrate basically over sphere at infinity, and you can define then energy, linear, and angular momentum in that way. So you have to say, of course, this holds for many interesting asymptotically flat systems, and so energy and linear momentum hold actually very generally, and for angular momentum you need a little bit more of decay to be defined. So what about null infinity? Because I told you at the beginning, heuristically, so radiation, we would like to understand null infinity and explain something about radiation here, extract this from our space-time. So we would like to understand the Cauchy problem and then see how the space-time, the solution looks at null infinity. So I can also foliate my space-time not only by, let's say, space-like hypersurfaces like this. I can also foliate my space-time by null hypersurfaces. So, and I'm going to draw them like a cone. Of course, they have structure, but you can think of them as generalized light cones, for instance. So this is maybe U1. So you have this light, this null hypersurfaces, etc., that I can generate like that. And again, so when gravitational waves travel at the speed of light, they travel along these null hypersurfaces out to null infinity, and that's what we're interested in. So if you, the Bondi definitions of this, so the ADM definition that you just saw on the previous slide have something like an equivalent, well, have a corresponding definition at null infinity, and we call this the Bondi definitions. It goes back to Trautmann, Bondi, van der Borg, Metzner, and Sachs in the 1950s and 60s to define mass, energy, and momentum also at null infinity. Well, there's some more constraints probably you have to put there to make things work. I'll say more about it. A famous theorem, of course, in GR is that mass is positive. And so this was shown by Shane and Yao in 1981, and then also by Ed Witten separately. And then in the Bondi case, this was also studied by Shane and Yao later. So first of all, energy, what's now the real good way to talk about energy? So energy controls the curvature, first of all, but what kind of energy? So we use the Bell-Robinson tensor quite often. So here's one solution to this problem. So we can think of the Bell-Robinson tensor. So this is defined as follows. So this is basically, it's a 4-covariant tensor field, but it's basically, if you look at that, it's a quadratic in the Wild tensor. So you look at the Wild tensor of your space-time, and basically the Bell-Robinson is a quadratic in your Wild tensor. It has a lot of nice properties. It is actually positive in this sense that if you plug in future-directed time-like vectors, so you get this positivity property, and it also satisfies the Bianchi equations. So here's just a notation for what I use for the Hodge duals. Maybe let me point out, so this was used heavily in the work by Christodoulou and Kleinemann on the Minkowski stability. So this is really the main object to control the curvature there, and nowadays by many other people as well. So let me also introduce the current. So if K, this Q now, the Bell-Robinson tensor I just introduced. So contract this now with 3 future-directed causal vector fields, and we obtain what we call the current in this case. So I'm going to call this J. That's my current. Then I can apply some divergence theorem on a bounded domain in the space-time, and I can also then find what is my curvature flux. So if d omega here is just the boundary of this, so if this contains a portion of a null hypersurface, so we remember that, with some affine tangent null vector field L, then the corresponding boundary term is indeed the curvature flux through this null hypersurface C. And we can write it down as like this integral. So this is the curvature flux we can define like that, associated to some null vector field L. So these are some important objects to think about. And often when you would like to prove, I'd say, control, so the Bell-Robinson tensor actually controls the curvature, and from there we can go on. So maybe back to the Cauchy problem for one tiny moment. So if you look at initial data of this type, so I have not yet told you how much decay you need, etc., for certain questions. So if you look at Christodoulou-Kleinemann's Minkowski stability proof and Zipser's generalization to Einstein-Maxwell case, so the initial data has this kind of form. So you look at the initial data where for large R, your G bar has a form like 1 plus 2m over R here, the first term, and it decays like, let's say, R to the minus 3/2, and the corresponding decay is also for K with some regularity. And in my generalization of this result, so I have less decay. So I only have a decay of R to the minus 1/2 here and some less regularity. And now you can ask, what do you need in order to see some interesting things in terms of radiation or memory effect? So it turns out, I mean, here you get all the information. And in fact, Christodoulou used exactly the last chapter of his book with Sergio to derive this nonlinear memory effect of gravitational waves. So not only you find the existence and uniqueness of solutions, you have a perfect description of how the asymptotic behavior looks like. So in my case, well, I do see some things, you can compute a few things, but in order to get the full picture, this is kind of hidden in the decay, which is very low, very slow decay here.
Just a comment, a question on notation. Subscript O subscript 3 means that's true for 3 derivatives of the quantities.
Right, so I mean, with each derivative, you go down by 1 power of R. R or U, I mean, well. So here are, let me also write down just the evolution equations, the constraints and the lapse, just to give you an idea. So, I mean, we can then write down, we said the Einstein equations decouple into constraints and evolution equations. So phi is just my lapse function. So I have an equation to evolve the metric G bar given by this right-hand side. I have an equation to evolve the second fundamental form Kij. And so here, this is actually the R on each space-like slice on the right-hand side. And if I choose a maximal foliation, meaning that the trace of K is 0, so the constraint equations reduce to this set of equations. And in addition, I have an equation for the lapse of a maximal foliation here to look like that. So, and again, so you can put this into hyperbolic form, etc., and work with that. Now, let me also mention just briefly the stability result by Christodoulou and Kleinemann. So this was a big breakthrough, of course. Question is, can you perturb Minkowski space just a little bit to get a global solution which is geodesically complete for all time? So, well, this is one very simple version of the theorem. To state it fully, you need a few more pages, but you could say that every asymptotically flat initial data, which is globally close to Minkowski, globally close in the sense with weighted Sobolev spaces, etc., certain norms have to be small enough. So this gives you a solution which is a complete space-time which is tending to Minkowski at infinity along any geodesic. So, and interesting enough, I was just a few weeks ago, I spoke to a few physicists like Strominger at Harvard, and they now talk all about the Chrysodoulou-Kleinerman space-time. So they are at the moment very much they are looking for solutions which are exact, there's no approximation, anything. And it turns out, as I said before, so the last chapter of this book gives you the most precise information about some interesting physical space-times. And of course, you can always try to, do approximations, etc. But it's interesting also to know if you maybe relax, go do something else a little bit, how does your solution really look like? So I mentioned the generalization by Zipser. Well, in my generalizations, you don't really see as much of radiation. You cannot really read these things off that well. There's many people that I'm not citing everybody who have worked on related problems. So let me just say this is actually interesting for us because we get a precise description of null infinity, and that's what I would like to stress also. Okay, maybe, well, just here on the blackboard, I already explained this, but we usually work with two types of foliations in this setting. So one is given by a space-like hypersurface, now it's called sigma here, which I call H on the blackboard, and also null hypersurfaces. So we will be interested in outgoing null hypersurfaces, and for simplicity, they look just like cones on my slide. Well, one thing again to remember, I use a maximal time function. The trace of this case is going to be 0. Each space-like slide is a complete Riemannian hypersurface with corresponding decay, and then I'm interested in